Hi everybody, it's Dr. Nigro. I'm here with the second in our series of screencasts dealing with projectile motion. This screencast is going to look specifically at projectile motion that is up and out from the original point of origin. All right, there's an earlier screencast that deals with clip problems and the introduction to projectile motion. So if you need to go back and watch that video, please do so. All right, so for our up and out projectile motion, this occurs when an object is thrown outward and up simultaneously. So we get both types of motion. So if we go back to our basketball shot, remember from that earlier video, right? The path looks something like this, all right? So as with the clip problem, the path that the ball traveled is called its trajectory. So that is the same, all right? The difference here is that it's curved because we've got two components. We've got this vertical piece and we've got our horizontal piece. All right, the key difference is we've got both of these initially. All right, whereas with the clip problem, it's only horizontal initially. All right, so similar to what we saw before, what causes the horizontal motion is the thrower. All right, and what causes the initial vertical motion is also the thrower. What causes the remaining vertical motion once the basketball player, in this case, lets go of the ball, there's gravity. All right. Does one component of the motion depend on the other? No. Just like we saw with our clip problems, they are independent. All right. The horizontal velocity is constant. All right. And the vertical velocity will be changing. All right, so I've got a very important concept box down here. So just to emphasize this, when working with projectiles, the horizontal motion and the vertical motion are independent of one another. Both are occurring simultaneously, but do not influence one another. All right, that really is the key concept in this unit. You have to keep those two components separate. All right, so we already did graphs dealing with a clip problem. So now let's look what those graphs would look like if we're talking about an up and out problem. All right, now you're going to see some similarities, particularly the horizontal motion. So again, this is our x component, all right, and it is constant. All right, so that means for our position versus time graph, all right, we're going to see it move in a diagonal way. All right, so we get a diagonal for our position versus time graph, and our slope, just like we saw with our clip problem, is equal to the velocity of that motion. All right, so if I asked you to describe what you see in this graph, all right, you could tell me that that object is moving forward with constant velocity. All right, now our velocity versus time graph that corresponds to this motion is going to show a flat line for our velocity, right? Because that value is constant. So we see a flat line and the slope is going to be 0. Now this y-intercept should be your velocity value, but we know that when we use log or pro, sometimes that's not the case. But theoretically, it should be. All right, for our vertical motion, which is our y component, all right, we should see changing velocity. All right, now the difference here is where we saw our distance versus time graph start up high because we were starting away and falling towards the ground. This time we're going to start low and the object is thrown up to start with and then comes back down to the ground. All right, so we're going to get a curved line that looks like this, a rainbow shape. All right, now it's still curved. Sorry about that. All right, and according to the plot, the object is moving up, slowing down, then moving down and speeding up. All right. For our velocity versus time graph, we've got velocity and time. All right, it's not flat. All right, instead it is going to be a diagonal, but it's going to look a little different than our clip problem because we're going to start up and slow down. So we go to 0, and then we're going to change direction and speed up. So it's going to look like this. All right, so we get a diagonal. All right, and the slope here is again equal to our acceleration. All right, and we know that that acceleration should be equal to, should be equal to gravity. All right, where's my eraser? There it is. I meant to put gravity up here. Gravity. All right, the y-intercept should be whatever that initial vertical velocity was that the thrower gave to our object. Okay? All right, so we're going to slide down. We're going to look at our problems again. We're going to be using the same organizer that we saw before. We're going to be using the same formulas that we had before. All right, so let's slide down to this problem. All right, Tyler tosses a ball to his friend Cam, who's standing 10 meters away. Cam catches the ball at the same height 3.5 seconds later. All right, draw a picture of this motion in the box below. Label any given information. All right, so we've got Cam and Tyler throws a ball to Cam. All right, now the distance between these two is 10 meters, and it's in the air for 3.5 seconds. All right, so what type of problem is it? This is an up and out problem. All right, if it were a cliff problem, it would start at the maximum height, and that would be all we would see. All right, so what can we fill in our graphic organizer based on this information? All right, well, Tyler and Cam are 10 meters apart horizontally, so that 10 meters is dx. All right, we're also told it takes 3.5 seconds for the entire motion to occur. All right, in addition, I know that there is no horizontal acceleration and that the acceleration due to gravity, the vertical acceleration, is negative 10 meters per second squared. All right, so the first question is, what is the horizontal velocity? So I'm looking for Vx. If I look at my graphic organizer, I have dx and I have time, and I know that Vx is equal to dx divided by time. All right, so I come over and I plug in 10 meters divided by 3.5 seconds, plug all that into my calculator, and I find that my horizontal velocity is 2.9 meters per second. All right, so 2.9 meters per second. All right. How long does it take the ball to reach maximum height? All right, so how long does it take the ball to reach this height? All right, now remember, the whole motion takes 3.5 seconds. All right, so the time to reach max height is going to be half of the original time. All right, so 3.5 seconds divided by 2. All right, or 1.75 seconds. So that's the time it takes to reach maximum height. All right, and you might ask yourself, well, why does that matter? All right, well, it matters because we know what's going on in terms of the vertical velocity at maximum height. We know that it's 0 up there. All right, so it's a useful piece of information to have. All right, what was the initial vertical velocity of the ball? All right, so again, like I said, at maximum height, I know that V final is 0. So if I know the time, V final, and acceleration, I can solve for V initial. All right, so I'm going to use my V final formula and then plug in 0 for V final. V initial is my unknown. And then I have negative 10 meters per second squared times 1.75 seconds. All right, if I do the multiplication and then rearrange, I find that the initial velocity was 17.5 meters per second. So that's the initial velocity upwards that Tyler used to put the ball into the air. All right. Now it wants to know, well, what was the maximum height of the ball? All right, so I know V initial. I know the time it's going to take me to reach maximum height, and I have acceleration. With that information and my distance formula, I can solve. All right, now there are a couple different ways to do this. You could solve for V average and use that formula, or you could just use your distance formula. I'm going to use the distance formula because I know that's the one most of my students like to use. All right, so distance is equal to 17.5 meters per second times, whoops, that time is 1.75, not 0, seconds, plus 1/2 negative 10 meters per second squared times 1.75 seconds squared. All right, so with all those values plugged in, I use my calculator and solve, and I find that maximum height is 15.3 meters. All right, so 15.3 meters is my maximum height. Excuse me. All right, now it wants to know what was the final vertical velocity just before Cam caught it. All right, so remember, we found that the velocity up here was 17.5 meters per second. That's what we did up in part D. Now it's asking, well, what is the velocity here? Well, remember from our free fall unit, whatever velocity we have initially has to be there at the end. So that's going to be negative 17.5 meters per second. So there's not a calculation needed here, just a recognition of what's going on in terms of the motion of the object. All right. All right, so G says draw a vector diagram in the box to the left that shows the horizontal and vertical components of the ball just before Cam caught it. Include labels for the components you know. Excuse me again. All right, so we have the ball moving horizontally at 2.9 meters per second. The ball is also dropping vertically at 17.5 meters per second. Sorry. Excuse me. Here's my resultant. Now my resultant is going to be found using Pythagorean's theorem, all right? All right, so VR squared is going to be equal to VX squared plus VY squared. So we've got 2.9 meters per second squared plus 17.5 meters per second squared VR squared. So if I plug that into my calculator, do the squares, and then take the square root, I find that my resultant velocity right before it hits the ground is 17.7 meters per second. And since we're pointing down and to the right, I'm just going to list southeast as my direction. All right. So I know that you guys probably hoped that all the vector stuff was going away now that we finished our vector unit, but that's not the case. We can also use vector addition to figure out what the overall velocity should be of these projectiles right before it hits the ground. Okay? All right, so that gives you an example of how to do an up and out problem. And just like the cliff problems, there's a lot of combinations that we can go through here. So please give them practice. Let me know if you're having any problems, and I'll see you in class.